So I just want to talk briefly about cardinality and some special ideas inside of cardinality. Um, so remember that cardinality is the number of elements that are in a set. All right, and we denote it generally. We'll have a set S, all right, and we denote it as like the absolute value of S. All right, that just means to count up the number of elements in the set. Now we're going to have these two terms, and these two terms they're actually very important inside of mathematics, and they're important ideas to understand inside of computer science, and we'll talk about that in just a moment. A set that is finite or has the same cardinality as the positive integers is called countable. And if a set is not countable, then it is called uncountable. All right. And we're not going to get into too much into proving countable and uncountable. If you study math or you end up studying more math, you will actually do that. That'll be kind of like kind of an important proof. What we want to do is just understand what it means to be countable or uncountable. Okay. So one, we have this first idea if it's finite. That is that um, it ends, right? So an example of a countable set, so for example, would be S, and we just have 1, 2, 3, 4. Okay, right? And so that means that the cardinality of S equals 4. That's finite, and so hence that's countable, right? But then there are infinite sets that are in fact um, countable as well. Okay. And what we say is that a set is going to end up having the same cardinality as another set if it's in one-to-one correspondence. And like I said, we're not going to get too much into that with another set of the same cardinality, right? But it's kind of going to be helpful for us to understand what kind of sets are countable, right? That the idea that I can actually count the elements. I may never stop counting, but I'll still be able to count them. Okay. And so, like, for example, we'll take the example, the positive integers, right? And that's the set, right? 1, 2, 3, 4, so on and so on and so forth. Okay. And that's infinite, but it's countable because I could just go in and count it. All right. Now, if I take z, the set of integers, and I add 0 to it, that actually is also going to be countable as well, right? It's 0, 1, 2, 3, so on and so on and so forth. And the reason why is basically what I'm going to do is I can set up a function, all right, a one-to-one and onto function that'll in fact map all of z plus onto z plus 0. Okay, so the element z plus, right? We've got right 1. I want to map 1 onto 0. I want to map 2 onto 0, onto 1, 3 onto 2, so on and so forth. All right. And there's a really simple bijection that'll do that. And I'll leave it up to you to prove that it's a bijection. But that's just f of x equals x minus 1. All right. And we just define f as going on from z plus, the positive values, to z plus 0. Okay. And that'll actually create that one-to-one correspondence. And so consequently, z plus 0 is actually also countable. In fact, the integers end up being countable, all right? Even though they're both negative and positive. So we go dot, 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 right? -3, -2, -1, 0, 1, dot, 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 so on and so on and so forth, okay? And I'll leave that up to you to kind of think about what the bijection is going to look like for that. You can find it pretty easily online too if you want to, all right? Another one actually that's also countable, and this proof is inside of your book, we're not going to get into it right now, is the set of all rational numbers. All right, a very famous proof to show that the rational numbers are in fact countable. So, right, we've got like anything, the set of all numbers x belonging to the reals, such that x equals a over b, with a and b belonging to the integers. All right, that's my set of rational numbers, and it turns out that they're also countable. There's an infinite number of them, but they are in fact countable. All right. And the reason why countable numbers are so important is because with computers, we can actually work with countable sets. When it comes to uncountable, and we're going to see those in a minute, uncountable sets computers don't work with very well. Computers work with iterations, discrete numbers. That's why we're doing discrete math. And so consequently, computers aren't going to work with uncountable sets. They'll only work with countable ones. All right. So if we have anything that maps directly onto, say, for example, the rational numbers or the integers, the positive or negative integers, that's fine. That works totally fine for working with the computer. On the other hand, when we start looking at uncountable sets, we're going to have to turn those uncountable sets, we're going to have to like kind of fake them. We're going to have to fake them into countable ones so that the computer can actually work with them. All right. So I'll give you an example of an uncountable set. The most common